In this video, we will learn how to read and interpret graphs to find limits and function values. Before we jump into our 3 examples, I'm going to have us refresh our memories on a couple key things, mainly with notation. So the first one is this notation that says the limit as x approaches a from the left. So remember, this negative exponent is representing as we're approaching in from the left-hand side of f of x. Then our second notation says the limit as x approaches a from the positive side, or the right-hand side of f of x. And then our limit as x approaches a, where there's no superscript here, and what that means is the overall limit. For the overall limit to exist, that means that the limit from the left has to equal the limit from the right, and if those limits were not equal, then we would say that the overall limit does not exist. So the key things that we're looking at here is the superscript. So if we go to highlight it, the superscript, if we're approaching a from the left, means the left with the negative side, or the left-hand side, as x approaches a from the positive side, which is representing the right-hand side. Or if we have no superscript, then what this means is an overall limit. And the key thing here is for this overall limit to exist, it means the limit as x approaches a from the left of f of x has to equal the limit as x approaches a from the right of f of x. Now, if the limit as x approaches a from the left of f of x does not equal the limit as x approaches a from the right of f of x, then we would say that the limit as x approaches a of f of x does not exist. And we tend to abbreviate does not exist with DNE. The other thing I want to draw your attention to is that limits are equal to the y values. So when we're evaluating a limit, it's like what would happen if you were to evaluate a function. You're having a limit value as x approaches a number of some function f of x. Well, for that to be equal to something, that's going to have to equal the y value, since f of x is representing our y value here on our y-axis. So on each one of these graphs, as we're finding limit values or even function notation values, which is like example h here, which says f of a number, this is an example of a function value, not a limit. But regardless of which one we're looking at, for each one of those, we're looking for a y value off of this graph that would make this equation, or this sentence, mathematical sentence here, true. So let's look at our first example. The first one says the function f of x is shown above. Use the graph of f of x to answer the following. So there's a lot of sub-questions here, but we're going to see that these tend to go quickly because they help us answer the next one kind of after it. So we have a bunch here because we need them to answer kind of the overarching questions. So the first one, part A, says the limit as x approaches -7 from the left-hand side, because of the negative exponent, of f of x is equal to what? So what I'm going to do is I'm going to go to my graph where -7 is, and we're looking at this value right here on the x-axis. So our x value that we're looking at is -7, and in part A, they want the limit from the left-hand side. So as we can see, there's kind of 2 pieces to this. Neither of them have a closed circle, which does not matter if they were open or closed. Now, of course, they both cannot be closed, otherwise this would not be a function, since it would not pass the vertical line test. But it doesn't matter that they're both open. The open and the closed circle actually has nothing to do with a limit. But when we're looking at the limit as we approach from the left, we're trying to see which branch of this has a piece that is coming in from the left-hand side. So if I look at the top part of this, there's a piece that is approaching in from the left-hand side, and this is the part of the graph that we're going to look at for the limit as x approaches -7 from the left. Now, as we're approaching in from the left-hand side, we're approaching this open circle here at -7, but more importantly, the y value that goes with that is +2. So what that tells me right off the bat then is that the limit as x approaches -7 from the left-hand side of f of x is going to be equal to +2 then. And we can repeat this process for what's happening in as we approach in from the right side. Now, as we approach in from the right side, I can't use this piece of the graph since there's nothing over here to the right, but what I can use is this other bottom piece down here, since there's a piece of the graph that's approaching in from the right-hand side. So it's coming towards it from the right-hand side. Yes, it's going to an open circle, but it wouldn't matter if this was open or closed. What I'm paying attention to is the fact that the branch here is approaching from the right-hand side, and it approaches a y value of -2. So what that tells me then is that the limit as x approaches -7 from the right-hand side of f of x is going to be equal to -2 then. In part C, what it's asking is the limit as x approaches -7 of f of x. So there is no superscript there is no right or left side, so what this is going back to is our overall limit that we talked about down here. Now for an overall limit to exist, it means that the limit as we approach in from the left side of that function has to equal the limit as we approach in from the right side, and if they're not equal, then we say that the limit does not exist. Well, if I go back and look at this, my answer to part C is going to rely on what my answers to parts A and B were. Well, in part A, we found the limit from the left, which was +2, and in part B, we found the limit from the right, which was -2, and since 2 does not equal -2, then the overall limit then cannot exist. So we say that the limit as x approaches -7 of f of x does not exist. I'm going to abbreviate that with D and E just because I don't have a lot of space here. Now, if we were asked to justify this, I'm going to add the justification up to this left side over here. So the justification is because the limit as x approaches -7 from the left of f of x. So make sure you always have a function input into our limit. It wouldn't make sense to just have a limit with no function input, so I can't have what I say floating limits can't exist. So because that limit from the left does not equal the limit as x approaches -7 from the right-hand side, oops, sorry, I'm going into the first part of the question, of f of x. So since the limit as x approaches -7 from the left of f of x does not equal the limit as x approaches -7 from the right of f of x, then the overall limit here does not exist. Okay, part D says, what is f of -7? Well, this has nothing to do with a limit at all. This is asking for the coordinate pair then. So at -7, what is the y value where I would have a filled in circle? Well, if I look here on the graph, no matter where I look on this graph then that we have, -7 has no filled in circle along here. So as we go through this, I have no place that has a filled in circle along this graph at -7. Here's an open circle, here's an open circle, and then anywhere else that I look that I can see this graph, there is no filled in circle. So what that tells me is that this function value is undefined. So what we would say here is that f of -7 is undefined. Let me scroll up so we can make sure we're seeing it all. Oops. Now, it's really easy to want to think that does not exist and undefined might be interchangeable, but they're actually not interchangeable for us. So does not exist applies to a limit because that limit value itself from the left and the right, if those two are not equal, then the overall limit can't actually exist, versus undefined is referring to if something is defined on the graph or defined in a function notation. And so because there is no filled in circle at -7, then f of -7 is undefined then. Okay, let's look at our next couple. So I'm going to scroll down so we can see E, F, and G, and then I'll go back up to the graph to draw on it as we do them. So part E says, find the limit as x approaches -3 from the left of f of x. So part E is starting with -3 on our graph, and we're mainly focusing in what's happening on the left-hand side. So if we go back up to this graph, I'm going to go back to our highlighter so we can see it, and why don't we do it in blue this time? So at -3 here, what I'm looking for is on this graph, where am I approaching in from the left-hand side? So if we scroll up to see the entire graph, we can tell that the only piece that's happening at -3 is this area right here. And from the left-hand side, we're looking at this segment that is literally to the left of -3, and it is approaching, yes, an open circle, but that open circle is happening at -5. So what that tells me then is the limit as x approaches -3 from the left is going to be equal to -5. So we go down here, we can write in -5. Now we can do the same thing from the right side of -3. So the limit as x approaches -3 from the right, we're paying attention to this same area ultimately as it comes in. We're dealing with that same y value there of -5. So although E and F look similar to A and B, what's going to end up being really different is G here, because the limit as x approaches -3 of f of x is based off of my answers to E and F. And since my answer to E and my answer to F were both the same, since both the left limit and the right limit are both equal to -5, then the limit as x approaches -3 of f of x, so our overall limit has to be equal to -5. And the way we would justify that is similar to the way that we justified part C up here. The difference is going to be that I actually get an equals to sign now. So I'm comparing the limit as x approaches -3 from the left of f of x, don't forget to have your function, is equal to the limit as x approaches -3 from the right side of f of x. Since both the left and the right were equal to -5, then the overall limit is equal to -5. And now when we look back at the graph, it didn't matter that they both go to an open circle. What matters is that both the left and the right side meet up at the same open circle. Now part H kind of goes with the prior three parts. It's saying what is f of -3. So again, this is not asking us for a limit. Part H is asking us for a function value just like it did in part D. So in part H, what I'm looking for is where is the filled in circle on the graph, or is there one at all? So if I look at the graph at -3, there is no place where I have a filled in circle at all along the vertical line x equals -3. So just like in part D, f of -3 is going to be undefined, since there is no filled in circle at all when x equals -3. Now let's say there was a filled in circle somewhere else, then I would take that y value to match with it. And we'll see examples of that as we keep going. Okay, let's look at part I. So part I says the limit as x approaches -1 of f of x. Now we notice we didn't start off with a left or right hand limit this time, which is okay. But what this means though is that technically I have to find both the left and the right limit first before I can actually answer this question. So let's go back to the graph and look at what's happening at -1. If we go switch over to a highlighter, why don't I use green this time? So we're looking at what happens as x approaches -1. Well, from the left-hand side here, that's this part of the graph that I just highlighted that's approaching +5. And then the right-hand side of this graph is approaching up here at +8. What that tells me then is the limit as x approaches -1 from the left is equal to 5, but the limit as x approaches -1 from the right is equal to 8. And since 5 is not equal to 8, then what that tells me is that this limit does not exist. And I'm going to go ahead and add our reasoning. I'm going to try to fit it underneath. So the reasoning here is that the limit as x approaches -1 from the left of f of x, which happened to be equal to 5 in this case. Let's write out the numbers since we didn't have the two prior parts. But 5 is not equal to 8, which is equal to the limit from the right side. Oop. I think we just barely fit it there. So it's okay if they don't ask you to first find the left and the right limit first. It means that when you're asked for an overall limit, you ultimately are really asked what is the limit from the left, what is the limit from the right, and then see if those two limits are equal. And in this case, they were not. Now part J is saying, what is f of -1? So again, this is not a limit question, this is now asking for a function value. So I'm looking at the graph at -1 and I'm looking for the filled in circle, and in this case there is a place with a filled in circle, and that happens down here at -2. So f of -1 is equal to -2. So it's just kind of a side notation because we'll use this throughout the year, but remember this function value notation right here is the same thing as the coordinate pair, which says -1, -2, which matches the coordinate pair on this graph. So remember, when I have f of x that equals a y value, that tells me that my x here is -1 and my y is -2. Okay, let's look at our next set. So our next 4 examples are looking at what's happening as x approaches 3, either from the right, the left, or the overall limit. So if I go back up to the graph, let's switch, I guess I'll go to pink highlighter this time. We're looking at what happens as x approaches +3 here. So in part K, it's saying what happens as we approach 3 from the left-hand side. So as I come in from the left-hand side, we're on this section up here that just got highlighted, and we're approaching a y value of +7. So what that means down here is the limit as x approaches 3 from the left of f of x is going to be equal to +7. And if we approach from the right-hand side, we're also approaching +7. So the limit as x approaches 3 from the right-hand side is also equal to 7. So what that tells us then in part M is that the limit as x approaches 3 overall of f of x has to be equal to 7, and the reasoning being is because the limit as x approaches 3 from the left equaled the limit as x approaches 3 from the right. So if I'm going to write out that explanation, let's fit it down here. So our reasoning for part M is because the limit as x approaches 3 from the left of f of x equals the limit as x approaches 3 from the right of this function. And now I know our instructions don't say to justify, but I'm going to keep having us write that because it's going to become a very important thing in future lessons. Right now we're focusing on finding limits and function values, but later on we're going to start talking about continuity, and to justify if a function's continuous, you have to determine if the limit exists, and you have to explain that justification using proper notation. So every time we've written these, I've made sure we've been writing with proper notation, meaning we have our limit as x approaches whatever number we're approaching of f of x, so make sure you have an input, is equal to the limit from the other side of, again, make sure you have that input there. Okay, part N says, what is f of 3? Well, this is not a limit, this is what is the function value. So if we go back up to the graph, I'm looking for the filled in circle when x equals 3, and that happens right here at the y value of 3. So f of 3 then is going to be equal to +3. And again, we could write that as the coordinate pair then, 3, 3, which we can see on our graph. Our next set of examples is going to deal with what happens as x approaches 5. Well, so far I've had us pick values that had these open or these closed circles, or what we call a jump or a hole on a graph, but if we look at 5, I don't really have any open circles. I don't have any, as maybe you could say, gigantic filled in circles like I did at 3, 3, but what's more important is I have no open circles. So as I approach 5, let's go ahead and highlight it in yellow, I'm just looking at this straight line right here. There is no what we call discontinuity, there is no open circle happening here. So as x approaches 5 from either side, no matter which side I'm looking at, the left or the right side, both times we're approaching this y value of 4 then, from both the left and the right, which means then that the overall limit has to be equal to 4 as well, since the limit as x approaches 5, from the left of f of x equals the limit as x approaches 5 from the right, come on, there we go, of f of x. So it doesn't matter if they happen to be where these open circles or these breaks or these holes or these jumps, whatever you want to call them in the graph, I can find a limit anywhere. And I don't need a gigantic filled in circle to be able to figure out what's happening on the left and the right, or an open circle. I just need to look at, well, at that x value, what is the y value that is happening? Part R is asking for what is f of 5. Well, f of 5 is going to be the function value, so I'm looking for the filled in circle. Now, although it might not look as obvious as some other places, this filled in circle is happening right here at 5, 4, because there's not an open circle. So I'm assuming it's filled in since there is no obvious open circle like we've been seeing on other pieces of this graph. Okay, we have a couple more in this one. So part S says find the limit as x approaches 7 of f of x. Well, this is an overall limit, so I'm going to have you guys go ahead and pause the video now, and why don't you guys decide what is the answer to S going to be? Let's check part S then. So for the overall limit, I have to look at the limit from the left and the right. So I'm going to just find those kind of separately on their own right now. So let's first calculate the limit as x approaches 7 from the left of f of x. Let's see what that's equal to. So as we come in from the left of f of x at 7, we're looking at a y value of 1. And as I come in from the right hand side, well, I also reach that y value of 1. So since both the limit as we approach from the right hand side and the left hand side, since both of those limits are equal to 1, then the overall limit will be equal to 1. Now we've done a lot with this graph so far, and we've got 2 pieces left. So part T says, what is the limit as x approaches negative infinity of f of x? Well, how I found all of these was I started at what that x value is, and I kind of then looked to see what's happening with the graph there. Well, I don't have negative infinity on my graph, but what I am going to pay attention to is negative infinity is representing what's happening as I go off to negative numbers on the x-axis. So what I'm looking at then, as if this graph were to keep drawing, I'd have more negative x values here, but what I want to pay attention to is, well, what piece of the graph is furthest to the left? Well, this piece right here, I'm going to go ahead and highlight it. Let's see if I can get another color. No, I guess I'll highlight it in blue. So this piece, as I keep going to the left, is the straight line segment that's going up, and you can even see the arrow on there. So I'm going to go ahead and draw the arrow with our highlighting. This is the piece of the graph that I want to pay attention to. So as x keeps going to the negative infinity, kind of along the x-axis here, this graph is going to keep growing up and up and up and up and up forever and ever and ever. Now what that tells me specifically then, as x goes to negative infinity, which is what's happening down here, so as x keeps going this direction to negative infinity, the y value that I'm getting keeps growing larger and larger and larger, so the y value then is going to be positive infinity. So that means that this limit then is equal to positive infinity. Now we can do the same thing as x approaches positive infinity. So instead here of looking at the left hand side, I want to pay attention to what's happening on the right hand side of this graph. So if I were to highlight this right hand side in pink, it's this kind of horizontal line that we have going on. So there's no other pieces of this. This is the last branch on the right side. And as it keeps going and going and going to the right, well, it's just creating this horizontal line. So no matter how far I keep going to the right hand side, the y value is always going to stay at positive 1 then. What that tells me then is the limit as x goes to infinity of f of x is going to equal positive 1. So we can kind of see in these last 2 examples how it's possible to find a limit as x approaches positive or negative infinity, and sometimes those limits are equal to infinite numbers, and sometimes those limits could be equal to finite numbers depending on what's happening on the graph. Okay, let's scroll down and look at our second example. So again, we have a function f of x, which is shown above. It is a piecewise function, meaning I have multiple parts of this graph, or multiple pieces, you could say. I have a piece on this. Whoop. Let's get the circle ring back up. I have this piece to the left that's a horizontal line, then it's curving, there's some holes in there. I now have a vertical asymptote, so it's a little different. And then I have these other 2 branches right there. I'm going to have you guys go ahead and why don't you answer the first kind of couple questions here, A all the way through G. And I'm going to have you guys pause the video right now and answer A through G, and then we will go ahead and talk about those. Okay, so let's check A through G. So part A is saying, what is the limit as x approaches negative 6 from the left-hand side of f of x? So if we're looking at this, I'm looking at negative 6 on my x-axis, and as I approach in from the left-hand side, that's this horizontal line that's going towards negative 7. So what that tells me then is that the limit as x approaches negative 6 from the left of f of x is going to be equal to negative 7. Now from the right hand side, I don't get to keep going and say negative 7 since there's nothing over here to the right. Instead, we're using this other piece of this graph that's coming in as x approaches negative 6 from the right. We are at negative 4 then. Well, I found the left and the right limit. Chances are they're probably going to ask me for the overall limit next, and they did. So the limit as x approaches negative 6 of f of x then does not exist, and hopefully you wrote out the justification, and that justification being that the limit as x approaches negative 6 from the left-hand side of f of x does not equal the limit as x approaches negative 6 from the right-hand side of f of x. Almost fit it. Now in part D, we're looking for the function value. So what is f of negative 6? What that means on the graph is I'm looking for the filled-in circle. Well, I do have a filled-in circle, and that happens to be down here on the piece that's connected, yes, from the left-hand side, but it doesn't matter what it's connected to. It could even be a floating dot like we saw in the last example. All that matters is that it's looking for the piece that is filled in, which happens to be at negative 7. So f of negative 6 is equal to negative 7. And again, as a reminder, that's going to match with that coordinate pair then that we're seeing on the graph at negative 6, negative 7. Now, I'd mentioned this earlier that it doesn't matter if it's connected to the left or the right side at all, but what does matter is that they're both not filled in. So it would not be possible, in case you're wondering, to have both of them filled in. The reason being is we're assuming that this is a function, and to have a function it means I have to pass the vertical line test, which means every input has only one output. So I could not have two filled in circles then, otherwise this graph wouldn't even be a function. Okay, let's check parts E, F, and G then. So part E says, what is the limit as x approaches negative 4 from the left-hand side? So if we go back up here, I'm going to use yellow, we're looking at negative 4, which happens to be right there on the x-axis, and we can see that both the left side is approaching 0 and the right side is also approaching 0. So that means that my answers to both E and F are going to be 0, since both the left side as I approach in is 0 and the right side is going to 0. What that ultimately tells me is that the answer to G has to be 0, since the limit, let me scroll down, see if I can fit that there, since the limit as x approaches negative 4 from the left-hand side equals the limit as x approaches negative 4 from the right-hand side of f of x. Now, I know I didn't say to jump ahead and do H, but you might have done it as you kind of can see that H kind of goes with E, F, and G since it's dealing with the same X value. So H is asking you for F of negative 4, which is not anything to do with the limit, it's where is the closed circle. So if we look here, although both the left and the right were approaching 0, there is no filled in circle there. There's what we call an open circle or a hole. So 0, f of negative 4 can't equal 0. Instead, the filled in circle is happening up here, which is at positive 6 then. Why don't you guys pause the video again and try I through N. So finish off this second column in here and then we'll check those. Okay, let's check I through N. So I is asking about the limit as x approaches negative 1 of f of x. Now notice there was no left or no right again, it's just asking you for the overall limit, so I need to find those each separately. So my justification I'm going to write over here to the side, and we're going to see if our answer is a number or if maybe the answer does not exist. So to be able to answer this, I need to first find what is the limit as I approach negative 1 from the left. Now let's see what that value is. So let's scroll up to see our entire graph. So as we approach negative 1 from the left-hand side, that's this segment coming in right here, and that's approaching the y value of 2. So the limit from the left is equal to 2. And as we check the limit from the right, that also is going to be equal to 2. So what that tells me then is that since the limit from the left equals the limit from the right, then it means my overall limit exists and is equal to that value there, which is 2 in this case. Part J is asking me for a function value, so it's saying what is f of -1. So this has nothing to do with the left or the right or the limit, it just has to do with where is the closed circle, where is that coordinate pair filled in, or does it not exist at all. So if I go back up to the graph, I know I kind of wrote over it, so let's erase some of those just so we can make sure. But as I look up and down on this graph, there is no filled in circle anywhere else, and although the left and the right are equal, they're meeting at an open circle, which is not filled in. So what that tells me then is that this function value is undefined, since there is no place where we defined the coordinate pair then for -1 to go with. Okay, let's start talking about K through M. So K is asking us what is the limit as x approaches 2 from the left. So you might notice that at x equals 2 here, we have a vertical asymptote. We can tell that by the dotted line that's formed on there. And what we're looking at is, although we're never going to be able to reach this vertical asymptote, since an asymptote I get infinitely close to but don't actually touch, just like a limit, that what we're seeing here is that as I approach from the left-hand side, it's this piece that keeps going down further and further and further, so that actually is going off into -infinity, since it keeps going down and down and down. So no matter how far I keep following this along, the y value, which is the piece that our limit's going to be equal to, keeps getting negative. So our limit then is equal to -infinity from the left side, since the left side's going down. Now from the right side, let's see what's happening. Well, from the right side, I'm using this piece up here that keeps going up and up and up and up and keeps getting more positive over time. So that means that the limit as x approaches 2 from the right of f of x is equal to positive infinity, or just infinity. Now, -infinity definitely doesn't equal infinity, so the overall limit then does not exist, since they're going in complete opposite directions and they would never have a chance of meeting up. So if we were to justify that, we would say the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right. Now, part N is asking you for f of 2, which, yes, I have a vertical asymptote here, so chances are I probably don't have any filled in circle on here, although I could. On this graph, though, I do not have any place where it's filled in, so my answer to part N, I'm going to write it underneath, would be undefined. That's going to f of 2. Okay, we have a couple more left here. I'm going to have you do the same thing that we've been doing, so why don't you pause the video and finish off this third column, so O through T, and then we will check those. Okay, let's go ahead and start by checking our first 3 on here. So the first 3 are looking at what's happening as x approaches 5 from the left or the right. So we're paying attention to 5 on the graph. From the left side, as we come in, we're dealing with this section up here that's highlighted, and we're approaching an open circle, but more importantly, that open circle is at positive 2. So what that means is the limit as x approaches 5 from the left of f of x is equal to positive 2. And as we approach in from the right side, we're going to this other branch, which is, yes, a filled in circle, but the filled in circle does not matter. More importantly, or the only part that matters, is it's approaching the y value then of -2. So the limit as x approaches 5 from the right of f of x is equal to -2. Now part Q is saying, what is the limit as x approaches 5 of f of x overall? Well, this limit does not exist, and the reasoning is because the limit as x approaches 5 from the left of f of x did not equal, or is not equal to the limit as x approaches 5 from the right of f of x. Now part R is asking us for f of 5, so again, we're not dealing with a left, a right, or a limit at all. We're just paying attention to where is the function defined when x equals 5, or from a graph perspective, where's the filled in circle? So on our graph, when x equals 5, at 2, although the limit's approaching here, it's approaching an open circle. So that can't be it. There's no other place, but down here I have my closed circle at 5 comma negative 2, which means that f of 5 is equal to negative 2 then. Now the last two parts of this question are asking for the limits as x goes to negative infinity and then x goes to positive infinity. So I'm going to pull out, let's use the yellow highlighter for both of these. So as x goes to negative infinity, I want to look at the furthest part of this graph to the left-hand side, which is this horizontal line segment down here. So as x keeps getting negative and negative and negative, I am safe to assume that I am just plateauing at this horizontal line, which means the limit then is going to be equal to this y value of negative 7. So if I go down here and write, that means our limit as x approaches negative infinity of f of x is equal to negative 7. Now on the flip side, as x keeps going positive and I keep going down, we're looking at the furthest portion of the graph to the right, which is this straight line segment that keeps going more negative and negative and negative over time. So although x is getting positive and x is getting bigger as we go out to the right, what I'm paying attention to is the y value. So the y value keeps going down and down and down and keeps getting more negative. So this limit then is equal to negative infinity. Now, this one has a follow-up question that our first example didn't. It says, justify why x equals 2 is a vertical asymptote. Now, on the AP test, or on really any calculus test, when you're asked to justify or explain, they mean in proper notation. So I could not just say, well, there's a dotted line on the graph, and from an algebra class, I know a dotted line represents an asymptote. That's not going to cut it in a calculus class anymore. They really want to know what is creating that vertical asymptote there. Yes, it's drawn on the graph, but it's drawn on the graph because they gave it to you. But what actually makes it a vertical asymptote is the behavior that is happening around x equals 2. So there's actually two ways to justify this, and it doesn't matter if you use both ways or if you only use one way. One part of this is sufficient enough, but what's ultimately making this a vertical asymptote is what we talked about in parts K through M right here. Really actually just K through L. So because these one-sided limits went off to either infinity or negative infinity, that's what's producing this vertical asymptote. And I don't need both of them to justify this, I just need one of them. So one way to justify this would be to say, well, because the limit as x approaches, let's say 2 from the left, so if I'm just going to consider the left-hand side, equals negative infinity, that would be an okay justification. Or, if you want to prefer to use the right-hand limit, you could say the limit as x approaches 2 from the right of f of x equals positive infinity. Either of those justifications will justify why we have a vertical asymptote then at 2. So it's kind of a summary here. This is a review from a prior video. You just need a that got really messy, I'm sorry. A one-sided limit to equal infinity or negative infinity. So I actually don't need both. One of them is sufficient. In this case, I did have both of them, so I'm going to go ahead and write both of those for me on there. Okay, let's move on to our third and final example. So in our third example, again, we're looking at a graph. So it says the function f of x is shown above. Use the graph of f of x to answer the following. So I'm going to have you do what we've been doing. The best way that you guys get better at this is with practice. So I'm going to have you pause the video right now, and I'm going to say I want you to do A. So let's start with A and go all the way through H. So pause the video right now and do A through H, and then we will check those. Okay, let's go ahead and check A through H. So in part A, we have the limit as x approaches negative 5 from the left. So I'm looking at negative 5 on my graph. As I approach in from the left-hand side, the y value that's going with that is positive 4. Part B says, what is the limit as x approaches negative 5 from the right-hand side? So if we're at negative 5 and now we're approaching from the right-hand side, let's see there we go, the whole graph. So as we approach from the right-hand side, we happen to also be at positive 4 as well. So hopefully that's ringing a bell then, that the limit as x approaches -5 then of f of x, so the overall limit here in part C, has to be equal to 4, and the reasoning for this, I'll fit it up here, would be the limit as x approaches -5 from the left of f of x equals the limit as x approaches -5 from the right of f of x. Again, make sure you have proper notation. So the biggest mistake I see is that people forget to write the f of x. And I know it's really tempting to, because we're used to saying, oh, the left limit equals the right limit. So we write the limit part and we think we're done. But a limit does not make sense unless it has a function value. So a nice explanation I like to give for this is, you guys would know what it would mean if I wrote down that. So if I wrote down this right here, which I underlined, you would say, oh, that's the square root of 4. Okay, I know that the square root of 4 is equal to 2. That question makes sense to you. Now, that's just like what it means, well, not what it means, but that's just proper notation, just like we need a proper notation down here. When people write limit, and write, let's just say the limit as x approaches -5 from the left, and then they write equals the limit as x approaches -5 from the right, this is not good notation, so I'm just going to call it bad notation. Okay, this would lose you points on an AP test. This notation doesn't make sense. This is the same thing as a test or teacher giving you this problem and just saying, solve that. Well, I don't know how to solve this because it's just a square root. A square root doesn't make sense unless there's a number inside of it. So without a number inside of it, I wouldn't know how to find the square root of it. That's equivalent to somebody writing down the limit as x approaches something from the left equals something from the right. This notation doesn't make sense unless you have an input value here. So the difference here is the proper notation, so I'm going to say the good notation over here on the left side has the function inputted. On the right side over here, the bad notation, which we don't want to use at all, has nothing implemented. Okay? Yes, this is shorthand, but shorthand is not going to earn you any points on a free response. Okay, let's check part D. So part D says, what is f of -5? Well, this is not a limit, this is a function value. There is no filled in circle anywhere here, so f of -5 then is undefined. Okay, let's check E, F, G, and H now. So E says, what is the limit as x approaches -3 from the left-hand side? Well, if I go back up to my graph, I'm going to go back to the highlighter. What's happening here is we approach -3, which is another vertical asymptote like we saw in the last example. As it keeps going up from the left-hand side, it's approaching positive infinity. So that means the limit as x approaches -3 from the left of f of x equals positive infinity. And if I scroll back up, as we approach from the right-hand side as well, this piece is also going up and up and up to positive infinity. So, whoops. So the limit as x approaches -3 from the right of f of x is also equal to positive infinity. So this is a little different than what we saw in the last example. In the last example, we had one side going up and one side going down. Now both of these are going up towards positive infinity. So both the left and the right-sided limits are equal to positive infinity. So this is where kind of the discrepancy comes into play, and it really depends on what book you're looking at. So some books would say that the limit as x approaches -3 of f of x then equals positive infinity, because the left and the right are both approaching the same type of infinite value. So they're both approaching a positive infinity in this case. But you also have some books that could say that this does not exist because the left and the right-handed limits are finite. So either of these are acceptable answers on the AP test. They will never put both of them down there on a multiple choice, but I just want you to know that either of those are acceptable. And the reasoning before on why our example 2 was for sure does not exist was because one side was going to negative infinity and one was going to positive. But in this case, because they're both going to positive infinity, there are books that can argue, well, they're both approaching the same infinity, so both positive in this case, or some books that would say do not exist because the one-sided limits are infinite. All right, and I just want you guys to be aware of ultimately really kind of the two different answers you could get here. Okay, part H says, what is f of -3? Well, this has nothing to do with the limit at all. This is what is the function value. And again, there is no closed circle anywhere on there, so f of -3 is undefined. Okay, I want you guys to go ahead and why don't you try I through, what was that, -1? Oh, there's 1. Why don't you go all the way I through P and try those on your own first, and then we will check them. Okay, let's start checking these. So I says the limit as x approaches -1. So that's the overall limit then. So what's happening at -1 overall? So let's scroll up so we can see the graph here. If I go back to the highlighter at -1, so I approach in from the left side and I approach in from the right side, they are meeting each other here. So I'm going to write my justification for I off to the side. Actually, I'm going to do it below the problem. I'll write my justification. I'll try to fit underneath. So here, if I look at this and I go the limit as x approaches -1 from the left of f of x, that was equal to the right, and let's see what the value was. So as we came in from the left-hand side here, this is approaching +3, which is equal to what's happening from the right-hand side. So because those are both equal then, don't forget your f of x, then the overall limit then is equal to +3 as well. Now in this problem also, this might have been the first example we've seen with this, where both the left and the right-hand side are equal to each other, and there's a filled-in circle there, which means that the function value, so f of -1, equals 3 as well. And now I think in the first example we did see something like that already. Okay, let's check k through the end now. So k says the limit as x approaches +1. So we're looking at a different portion of this graph now. So if we go back to the highlighter, let's use pink this time. So as we approach +1, from the left-hand side, it's approaching 7. Then from the right-hand side down here, we're approaching -2. So this is back to one of those examples where the left and the right are not going to be equal to each other. So the left was approaching at +7 up here, and the right was approaching at -2 down there. So what that means then overall is the limit as x approaches +1 then of f of x does not exist. And the reasoning would be that the limit as x approaches 1 from the left of f of x does not equal the limit as x approaches 1 from the right of f of x. Now f of 1 is now our function value question, so where is the filled-in circle? That does happen to be down here at -2. And just as a reminder, that's matching up with that coordinate pair then, which is 1, -2. Okay, our last two finite limits. So O says that what is the limit as x approaches 4 of f of x? Well, for me to figure out what this limit is, I really need to know what the left and the right is doing. So let's calculate these on the side here. So let's first find the limit as x approaches 4 from the left. So 4 is right here. As we're approaching from the left-hand side, we are down here at -5. But when we approach in from the right-hand side, we are up here at -2. So in this case, these are not going to be equal to each other. Let's see if I can fit this. Limit as x approaches 4 from the right. Ooh, that barely fit. So since the left side was -5, the right side was -2, that left and the right definitely are not equal to each other. So this overall limit then, that got messy, does not exist. There we go. Or DNE for short, since as we can see we don't have a lot of space on here. This is what we call on a graph as a jump, and we'll talk about kind of that vocabulary and those names for it when we start talking about continuity. Now the next piece of this before we get to our last two limits on here is what is f of 4? Well, f of 4 is the function value, and if I look on this graph, there's nothing up here. Although it's approaching -2 from the right-hand side, that's an open circle, so my function value has to do with the filled-in circle, which is at -5 then. Okay, the last two pieces of these are the limits as x approaches -infinity. So as we approach -infinity, that's what's happening is this graph keeps going off to the left. So the last branch of that is going towards this horizontal asymptote here. So this graph is approaching, although it's not plateauing. So in our prior two examples, we saw a graph that just had a horizontal line going straight out and it was already plateauing. But this is going closer and closer to this horizontal asymptote. So what that means then is that limit is going to be equal to 2, since that's where the horizontal asymptote is at. Likewise, on the right side, as x goes to +infinity, the last piece on here as this keeps going is also approaching the horizontal asymptote, which is at +2 as well. Now the last two examples we have on here go back to justifying types of asymptotes. So I'm going to have you guys pause the video and do S on your own right now, because we saw something like that in the prior example. Okay, let's check what part S says. It says justify why x equals -3 is a vertical asymptote. So again, yes, I can see from the graph that there's a vertical asymptote here because there's a dotted line. I cannot use that as a justification. Instead, it goes back to what's happening on the left and the right-handed limits for this. So parts E and F here is actually really going to be our justification. So one way to justify this would be to say that the limit as x approaches -3, that is a 3 there, from the left of f of x equals infinity, or you could say that the limit as x approaches -3 from the right-hand side of f of x is also equal to infinity. Now again, you only need one of these to justify it. I just need one of the one-sided limits to be infinite, either positive infinity or negative infinity. Okay, part T, our last example here, says justify why y equals 2 is a horizontal asymptote. Well, that has to do with the limits as x approaches either positive infinity or negative infinity. Because as we can see from the graph, what's really creating a horizontal asymptote here at y equals 2 is the fact that as I go off to negative infinity, this graph is plateauing, and as I go off to positive infinity, it's also plateauing. So our justifications here could either be the limit as x approaches negative infinity of f of x equals 2, or we could say the limit as x approaches positive infinity of f of x equals 2 as well. And again, you only need one of those to technically justify this, either the limit as we go to negative infinity or the limit as we go to positive infinity, which is why you can actually see two different horizontal asymptotes on a graph, because the left side might go to plateauing to some number and the right side might plateau to a different number. That is the end of how we can evaluate limits given a graph.